Anyway, if I can keep this thing on my ear, you'll be able to hear me. Yeah, I'm an associate editor for Sky and Telescope, and before I get into our survey here, I just wanted to reach out to all y'all on at Stellafane here, in that, we'd like to get more telescope making articles in the magazine. And the thing is, none of us on the staff are telescope makers, really. I built one myself. But I mostly like to image. So if you'd like to see more telescope making in the magazine, send me your pitches at swalker@skyandtelescope.org. Okay. Now let me put on my other hat here, which is this is my morning job, where we partnered together to map the sky in hydrogen alpha. Do I get a clicker or something to go forward? Thanks. How's this work here? Okay. Anyway, the MDW Sky Survey is a partnership between three amateur astronomers, myself, Dennis DeSico, and our friend David Middleman, who I believe he was visited Stellafane a few times. Do you know that at all? Or? Okay. Anyway, we met basically through the ATMOB in Boston. Dennis is a member, and I occasionally show up. And David was a member, too. We got the idea to image the sky in hydrogen light at 3.17 arcsecond resolution with 4 hours cumulative exposure per field. Now, 3.17 arcseconds might not sound terribly high resolution, but it's high enough that you can resolve a lot of small-scale features that aren't visible in a lot of the current surveys dealing with this particular thing. Anyway, it grew out of several interests. Dennis and I had been working together since the early 2000s, and one of his passions has been the hydrogen sky. As mentioned, it's basically the building block of everything, and it's the most prevalent gas in the universe. So stars are born from hydrogen. Where you're seeing hydrogen alpha glow, that's where stars are eventually going to form, or where they died. Anyway, our first project was mosaicing 15 frames spanning 4,000 square degrees, or about 10% of the entire sky. And we published that in S&T in April of 2009. This was our result. It's a fairly low resolution there. What was that about? No, the first one was with a 50 millimeter. This is the first one. Okay. Anyway, fairly low resolution. But we went deep enough from Dennis's backyard in Sudbury, Massachusetts, which is rather light polluted, to be able to pick up a lot of this faint filamentary structure in Orion and the surrounding region. If you look at this image, you can see the Milky Way cuts a swath across from the top to the bottom left of the image. And those are like the Seagull Nebula at the bottom, Rosette and Cone Nebula, and you go all the way up into Auriga with IC 405 and 410. Not to mention, to the right you have the California Nebula, which looks a little bit more like a scimitar to me in this depth. And you can just pick out the Pleiades on the middle right there. The big structure at the bottom right is called the Eridanus J. Anyway, it's a faint part of the same association that produced the Orion Nebula, which is the small area right in the middle there. So to give you an idea of what that field was like, this is pasted onto an all-sky image produced by our friend Tunç Tezel from Turkey. He loaned us this image so we could display what we were showing. So we had good luck with that, so we decided to step up to a larger lens. Dennis acquired a 110 millimeter lens, and we planned a 36 frame mosaic with 19 degree fields on each of the frames. Anyway, again, we settled for about 4 hours, because that's fairly deep, and we used a CCD, back when CCDs were the dominant toy, with fairly large pixels. I think these were 12 micron pixels. This was Dennis's setup after every night. He would get done shooting, and it was winter time. I think it was December through January we did this project, and it was below zero most nights. Yeah, this was our second version. Now this one goes even higher up, all the way up into Camelopardalis, and you're just touching on the bottom of Cassiopeia at the very top right there. At the bottom left, we're going a little further south down into, I believe that's Canis Major and maybe the tip of Pupus. But again, it also is, we went with the higher resolution, we're actually able to resolve smaller filamentary details. And that comes important in our next project. Okay, as you can see, the stars are kind of getting out of the way, so you can see more of the faint nebulosity in the field. That's not light pollution, that's all bands of nebulosity. And this is pushed to really bring it out. There's a lot of gas in the Milky Way. So this gives you an idea of where Dennis shot this, was in his backyard, and we've aligned the image. This is actually an accurate representation of the image over Dennis's house. He took wide field photographs, and I aligned our survey images here to match the field of view of his lens. So if we could see with hydrogen alpha with fairly large aperture eyes, that's what you'd see in the night sky. Of course, it'd be red. So in 2005, Dennis and myself and our friend David were kicking around ideas on how to continue our H-alpha work. We were thinking about continuing into the summer, doing the summer Milky Way, and perhaps finding a different field to concentrate on. First, we began by experimenting with the 200 millimeter or 8-inch Officina Stellaire Ricardi-Honder astrograph. That's a mouthful. Anyway, we did a 30-panel mosaic of Cygnus in the summer of 2015. And this is me stitching together and processing all the data. Impressive field of view, and as you can see, the stars get even smaller. So we start to see even more small-scale features. Like here's the Veil Nebula, the entire Veil Nebula complex, and you're beginning to see a lot more of the filamentary structure in between the brightest regions of, 6960 or, anyway, I don't know the NGC numbers off the top of my head. So the results were promising, but there were some limiting factors of the telescope. Number one is the limits of New England skies. It's just not as dark as it could be, mostly on the West Coast or in areas not in centers of population. Also, the Ricardi-Honder doesn't quite have the field coverage that we would need for the large detector we were using at the time, which was a Kodak KAF 16803 chip, which is, I believe that was 52 millimeters on the diagonal, and it's square. It's a pretty large field of view, larger than a 35 millimeter chip. Okay, so the stars in the corners look pretty wonky. Also, the reflective optics required recollimation with changing temperatures, and if we were planning on doing this without having to be at the telescope, that's kind of a big problem, being able to recollimate the scopes each night. So while we were regrouping to discuss this, Dave suggested that why are we limiting ourselves to only a certain region of the sky? And he suggested we could perform a systematic survey of the sky shot remotely from a dark sky location using off-the-shelf technology. And that actually hadn't been done before. Most surveys, or almost all of them, were performed by professional astronomers with, funding and a plan and people to man these telescopes to get the job done. We were approached. We were going to be doing this with letting software essentially do most of the work. All right. And the other reason why we decided to shoot the entire sky was that all the color and H-alpha surveys that are publicly available are very low resolution. This is the Virginia Tech Spectraline survey, and also it combines with the Southern H-alpha sky survey atlas to produce this crude map of the H-alpha coverage of the entire sky, primarily along the Milky Way band. That's how this one's aligned. It goes really deep, but when you zoom in, it's very low coarse resolution. I mean, you won't see a lot of the what do you call it, popular deep sky objects like M27, M1. Too low of a resolution. They look like stars at this site. Anyway, so David already was a member of New Mexico Skies and had observatory space there. So we went on with a plan to move some scopes down there and get going. He also set up a few observatories for colleges and for private use. These are some of his surveys. Our survey scopes are on the left there. But he also set up the Millman Observatory at Middlebury College in Vermont, the Hutt Observatory in Eagle, Colorado, an observatory on his former property down in Dover, and a couple of other things now in New Mexico, including our project. So, as I mentioned, he has a 20-inch planewave there and an FSQ that we would do some follow-up exposures on. One of David's big projects was relocating and restoring a Bowler and Chivens 36-inch Newtonian. There's Dave. I guess groundbreaking for his observatory in New Mexico. This is the 36-inch that I just mentioned. Did I lose something here? There we are. Yeah, there's the 36-inch with a very small-looking Alan Slisky, who might be here somewhere. That was their big project. So after all of our discussions, our planning's commenced in the fall of 2015. We settled on a pair of Astrophysics 130 Starfire refractors as our primary instruments, combined with with the particular field flattener that they offered that allowed us to get to a faster focal ratio than it was initially spec'd. We were shooting at f4.5 versus the f5 it's normally stated at, I believe. And we get, through working with Roland, we managed to establish a good compromise across the entire field. So we have round stars all the way from the center to the corners of the fields. We're using these FLI ProLine cameras, CCD cameras, and also a pair of 3 nanometer H-alpha filters. Again, we're going down to 3.17 arc seconds of resolution. So Dennis went to work building the imaging rigs. The focusers were replaced with FLI Atlas focusers, and to eliminate issues with dust, particularly and flexure, he designed and machined custom filter holders and spacers. And instead of a filter wheel, we have the filters mounted in a custom holder, so that it's in a sealed system. These are all the parts as Dennis was machining them. And when they come together, there's the filter mounted directly in front of the CCD itself. The thing on the bottom left there is the adapter that leads to the FLI focuser, I believe. Is that right, Dennis? Okay. This is one of the scopes all put together as Dennis was testing it out. He painstakingly established where tilting the CCDs so that we got perfect stars across the whole field. And I don't have an image of it, but we had textbook-looking analysis images that look like a bullseye, showing the collimation was absolutely perfect. So this is the back end of the two APs. It's kind of impressive because back in mid 2010s, It was very rare to see two AP-130s in the same place. So planning and executing the survey required some custom software. We initially began by testing the software, the mosaicing abilities that were built into Software BISC's the SkyX program. But it turned out that the way it was programmed, it was made to do mosaics of a galaxy with a high focal length telescope. What we were doing is wide field, and we're basically, the problem with that is that the original mosaicing in BISC software didn't account for the curvature of the sky. It was fine when you're talking about a degree, but when you're talking about trying to stitch together hundreds of degrees, it really became problematic. And as you moved away from the center of the field, your field of view would rotate and you wouldn't get perfect coverage over it. So, who's it? Steve Bisc worked with us to program a new, more robust mosaic planner, allowing us to plot all the fields with the SkyX Pro's original, that overcame the limitations of the original thing. Here's one of our test mappings. This isn't actually an image of how we plotted out our final fields here, but it was getting in the right direction. And yeah, we got a lot of fields that way. And after months of testing, the survey began operations in mid-June of 2016. So here's the scopes on a pair of Software BISC. Which mounts are these? The MX Plus. All right. We're able to shoot, from dusk to dawn every night. The scopes required a peer flip, so the only little wonkiness between that is that some of the images are south up and some of them are north up. At least for the stuff that as we were shooting in the north here. Here's the observatory building where several of the other scopes are located too, including David's plane wave way in the back. There's an FSQ to the back left there that we would do some follow-up exposures with that I'll talk about shortly. And then the two survey scopes were closest to us here, closer to the north wall, so that we could get as far south as we could reach from New Mexico. And we were able to shoot down to minus 32 declination from this location. So essentially, we got 80% of the sky from New Mexico. As I just said, currently we've nearly completed the northern hemisphere all the way down to minus 32. This slide is a little dated in that we've actually completed all of this information, at least from where we could image from New Mexico. And the last scope is just shipped down to Chile today. This week it's supposed to be going. Anyway, our entire project will require, 4,120 fields in total. As of the other day, we have just over 3,200 completed. But the way we image, we don't target one field and stick with it. It's just basically, it targets the fields that are best positioned each night. So think of it as us having 4,000 buckets where we need to get 12 drops in each of them, and they slowly accumulate. So, not long after commencing the survey, though, David was stricken with an aggressive form of cancer. To help lift David's spirits while he was undergoing treatment, we decided to publish some of the early results that we have, put together a website so he could enjoy some of the fruits of his labor. It's a little tough to see, but I had stitched together a lot of our fields back in 2017. There's a lot of holes at the time. But as you see, it really gives you an idea of how the sky is slowly accumulating as we're building this. Okay. We got a couple of apods out of it too. In early 2017, I submitted this image of M31 going all the way, the area going all the way into Cassiopeia on the left-hand side here. That other object over there is called Sivan 2, and we'll talk about that in a moment. Unfortunately, David passed away in May of 2017. But the Middleman Observatories and the MDW Sky Survey continue operations with the support of the Middleman Family Foundation, and with the intent to see his projects to completion. Asteroid 16779 is named after David Middleman in his honor. I believe Dennis was able to choose that because it was one of the asteroids that he's discovered. The time span was estimated to be about 5 years to complete this. We were off by maybe a factor of 2. It's actually not going to be 10 years, it's looking like. But in the past 7 years, when I first put this talk together, should say 8 years, we've amassed 4.5 terabytes of data and completed nearly 80% of the project. Now, this is actually dated. I forgot to update this slide. As of today, we have 3,204 fields completed. Now, the other fields that aren't complete, still have between 10 or anywhere between 1 and 10 of the exposures recorded. And you'll see an animation of that accumulation in just a moment. As I mentioned, we're shooting each of these things as they're best placed rather than focusing on one field and following it till its end. It allows us to actually take advantage of the whole sky better each night. That way we're not forced to give up because this part of the sky is cloudy and this one isn't. It's able to chase around the sky to look for the best conditions. Like I said, 99% of the northern campaign is complete. We'd been reshooting some of the fields to improve perhaps, better background signal. Sometimes there was a little more moonlight than we would like. So, it was acceptable for what our original intention was, which was to map the entire sky in hydrogen alpha. This is what my desktop looks like when I open up the images each day. As I'm working on stitching these together, it can be pretty challenging, but fun. Here's some of my early results here. This is a big object called SH2-126. It's in Lacerda, and it's a really large nebula that you rarely see imaged all at once. And to give you an idea of how big this is the entire constellation of Lacerda from our survey data. It's actually really easy to put together entire constellations with this setup, and I'm really impressed by being able to see the proximities of popular objects to other objects. It really helps me understand the sky better and plan some other things. Here's something to give you a really good idea of how the larger scopes give you better resolution. Here's Civen 147 in Taurus, okay? It's a supernova remnant. And this was with our original mosaic that we did. And I believe this is the one taken with the 110 millimeter lens. Here's the same field with our survey data taken with the 5-inch scopes at 585 millimeters. And as you can see, they're the same depth. I mean, this actually, the telephoto lens that we used here was actually faster, and we got 4 hours of data from that. But because we're at a higher image scale, the stars kind of get out of the way, and you can really see some of that faint stuff that surrounds the other objects in the sky. And that's what I'm really impressed with. Here's again a comparison of the Seagull Nebula taken with the 110 millimeter lens, and here's the same thing with the 5-inch scopes. As you also look carefully, some of the smaller deep sky objects really start to pop out in it. This right here, I'm not sure if anyone can recognize this field, probably not. But to give you an idea, the brightest star in the field here is Vega, or Vega, how you pronounce it. This image shows the constellation of Lyra. And the M57 is right between, right where you would expect it over in this part, and it's a little overexposed. But here's a larger field of view showing the same region of the sky and heading out from Cygnus all the way out to Hercules. And you can see all these bands of nebulosity that emanate from, or seem to originate from, the Cygnus cloud. Here's all of Cygnus stitched together in H alpha with our survey data. It's a little dark in here, so it's a little too bright in here, so it's hard to see the fainter stuff. And here's this plots out the entire constellation. I've added some right ascension and declination lines, plus the constellation itself. This is Sagitta, a little further south. I really enjoy this field because I didn't know there was a big nebula that surrounds M71. Let me go back here. In the right-hand part there, well, as you can see, the lines are showing you the constellation of Sagitta. Right in the center of that is the cluster there. Does this thing have a laser pointer? No. Okay, anyway, here's this without the lines and a little bit more of the field of view there. The big blob over there is M27 at the upper right there. Then there's that nebulous cloud surrounding M71. Yeah, here's what's that? Cedarblad 218. I probably ruined that one, but there's a lot of fascinating structure in the hydrogen sky that I'm just captivated with. Here's a big region that covers from Perseus and Cassiopeia all the way, well, most of Cassiopeia really. I think this is all of the constellation. As you can see, there's the Heart and Soul Nebula. The double cluster is at the center left there. But you go all the way to the right there, you can see some of the lesser known nebula like Sharpless 2-157 on the far right there. Looks like a lobster claw. And there's that Cedarblad 218 I just mentioned. And the lower middle is the Pac-Man Nebula, or NGC 281. Oh, I'm sorry, back up for a second. There's that Sivan 2 Nebula at the bottom right. And you can see it here. Here I've plotted all of the constellations. I hope to eventually publish a book on showing each of the constellations in H alpha. That's one of my projects. Here's the double cluster, and as I mentioned to you, there's a lot of hydrogen nebulosity around here. And the double cluster actually is burning off a cavity in the cloud in this area, and you can just make it out with the red in the area around here. I added the color using the FSQ that we use for follow-up exposures. Here we are again with the Veil Nebula. This is taken with our survey data. But what's really cool is when you run some programs nowadays, it's fairly easy to remove the stars in the image, and it really makes the nebulosity stand out. There's a lot of faint stuff that unfortunately you can't see in this bright room that permeate this area here, and it's absolutely mesmerizing. I encourage you to check out some of these on our website at mdwskysurvey.org. I have all of the images in the slide available on this. Here's that Sivan again, number Sivan 2. It actually hadn't been photographed since its discovery in 1972. Dennis tracked it down. We've added some color from lent to us courtesy of Rogelio Bernal Andrea. And we're getting a little bit more towards Camelopardalis, which is on the left there, and the edge of Cassiopeia there on the right. What's interesting in this field is on the top right there is one of the main stars of Camelopardalis is barreling through space at a faster speed and creates a bow shock around it. I believe that's Alpha Cam, or one of those. Anyway, Heading south, here's the IC 443 and 444 and NGC 2174 down at the border of Gemini and Orion. If you look in the wider field here, this whole area, it actually, IC 443 is surrounded by a larger faint bow shock around this whole region here. And it really is apparent in the middle bottom there. You can start to see a lot of that filamentary detail. And as I push it out, it brings it out a little bit more. Here's this is maybe some of you were looking at this on Friday night or Thursday night when it was clear. Here's M16 and M17 and a lot of nebulosity in the surrounding area. This is another one that is surrounded by a larger bow shock. If you look at the along the left there, there's some, I guess the bright stars are burning off the hydrogen in the area and creating these bow shocks along around the region. Here's the California Nebula, which doesn't look very much like California in this depth. And here's the Crescent Nebula and Sadir or Sadir, or however you want to pronounce it, and a lot of the other nebulosity in the heart of the Cygnus. There's a Butterfly Nebula, is that IC 1318? Anyway, here's all of Cygnus plotted out, and the borders are established correctly. To give you an idea of the image scale here, like I was telling you, those low-resolution hydrogen alpha surveys don't resolve small-scale features like this. This is M1 taken with our survey scope. And that gives you an idea of what kind of, 3 arc seconds is not something to sneeze at when you're looking for little objects, too. Here's M83. Galaxies show up pretty well, particularly ones with a lot of star-forming regions. And as I mentioned, the image scale lends itself to revealing large structures not visible with lower resolution instruments. And this has led to a few of our papers that we've been party to publishing in the past few years. Turns out when you put these obscure nebula online, the astronomers who discovered them take notice. While assembling some mosaic fields, for example, in northern Cepheus, I noticed the bow shocks that continued through several fields. This big object here, and I ran this by Dennis, and he did a lot of hunting and tracked down the object, what turned out to be a supernova remnant, suspected supernova remnant, G107, blah, 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 blah. Anyway, it was first discovered on the Rosat X-ray orbiter, which was surveying the sky in X-ray. So our image was the first one recorded at optical wavelengths, and it led to the actual identification of areas where they could take spectra of the object and determine the actual identity of it. So it's no longer a suspected, it's a definite supernova remnant. Yay us. Anyway, and here's the paper that was published based on that. We actually published a few papers from a similar fashion. Here's another object called a supernova remnant called G70-21.5. Rolls off the tongue, doesn't it? Anyway, here's a paper on its study and discovery. Another interesting feature that we stumbled across was another astronomer contacted us when he heard about our survey and asked us, do we see something near M83 or M82 up in Ursa Major? And I said, well, yes, there's this odd line here. And he was surprised that I said that and intrigued. He goes, follow this. And this was an object that they had discovered a few years back, but we were able to map it and publish a paper on it. It's a 30-degree ultraviolet arc, and ours was the first one discovered, seen in visible light, not ultraviolet. So this is the whole, it gives you an idea how big this thing is. It's very faint, and it's like maybe a degree and a half away from the M82 and heads all the way into towards, I guess it heads towards Cepheus. There's a lot of these filamentary structures in the sky, and they just fascinate me. So whenever I stumbled across these while calibrating our data each morning, I'd note some fields that I'd like to explore a little more. And when I had time, I'd stitch them together, and like this. Here's a recently discovered supernova remnant in Monoceros. It was discovered again in radio wavelengths. I'm not sure. It's not the bright object in the middle, but the fainter thing to the lower right of that. I took some, I examined our data closely, and I noticed there was a couple of little blobs in here. But when you remove the stars, some things become a lot more apparent. I'm sorry if you can't really see it, but there's a faint shell in the middle here that I did a lot of follow-up on. It turns out it's a supernova remnant G181.1 plus 9.5, discovered in 2016 at radio wavelengths. I confused another one in a different slide, sorry. This was the first optical confirmation of it, and we recently just published a paper last month on it, June. Here's a enhanced version of it. I shot it in H-alpha and O3, and we were able to push this out a lot more. That plots out where the nebula is a lot better, G181. So, again, as we've been completing a lot of this data, I was able to return to some fields that we'd done before, like that Orion area. Here's our 2009 image that we initially took at it. And I restacked our data. By the way, 500 fields is fun to manually align. This took me several days just to, using a program called PT GUI, where you actually have to select alignment stars, 8 of them on corresponding fields. Do that. That would be almost 2,000 times, because I had to do it on all 4 sides. So anyway, here's a really deep view of the Orion Eridanus bubble again, taken with our current data. To give you an idea, when you zoom in, there's a lot of fine structures in here, including like large columns that are being evaporated, pointing back directly towards, M42. This is in the southern part. This is the border of Lepus and Orion. Rigel is the bright star at the top right there. So when I remove the stars, all those towers really become a lot more apparent. And as we zoom in on it, it's really fascinating structures I was very unfamiliar with. And here it is in color. In winter 2022, we brought on a couple of people to help us manage moving the scopes down to the south. David Saliski and Arnie Hendon. David was our project manager, and Arnie Hendon was brought on. He was actually working with us for a while, but he mostly does a lot of the programming for reshoots and for plotting our new fields when we move the scope to the south. We chose OBSTEC, El Sos Observatory in the Chilean Andes to host the scopes. They have a lot of clear skies, and it turns out they have a really good seeing down there too. I don't know why I keep on losing. All right. So at the same time, David had known Professor David Siminovich and worked with them to partner with us to help disseminate our data and make it more freely accessible. Yeah, we can host a website, but working with the professional astronomy community will give us a lot more, a better reach, really. They're currently, the Columbia students are currently refining the photometric and astrometric precision of the data, things that we didn't consider in the first place. Our job, our initial project was to map the sky in H alpha. The only thing that we really thought about the stars were they round? Check. In focus? Double check. Well, it turns out you can still do some good astrometry and photometry, even though some of these images were taken years apart. Since we've been going since 2016, some of our fields have a baseline of 7 years or more between the first exposure and the last exposure. Unfortunately, not the ones with stars that move. I checked. Ironic is the one field that has a Bernard star in it, we happened to shoot all of that within 2 weeks. The one that I wanted to see some movement. Anyway, here's some of the astrometric reduction that they've been doing at Columbia, and photometry, refining the process on it, and calibrating these, I believe, to the pan-stars R band. Here's a measurement of H alpha color versus galactic latitude. Obviously, as you get farther away from the galactic latitude, it varies as expected. And as, of course, mapping the filamentary structure of the gas in the Milky Way. Daniela Fermin was working to produce a map of this. I don't know if she's still working with Columbia right now. But anyway, also trying to find a good fit for the astrometry in this was tricky too. Because of the wide field coverage, and I'm not sure what the problem was, but they finally figured it out. Tweak number 6 seems to work best. So as we moved scopes to the south last year in August, AP1 started imaging our southern fields. Doesn't look very far south, but this is just below where we could image from New Mexico before. That's the Cat's Paw Nebula, and this is in the feet of Scorpius. The Bear Paw Nebula, sorry. All right. Over here this is the Prawn, a little further down in Scorpius. I like that tower in the middle. And here's Eta Carina. We're starting to pick up the really big, bright stuff. Funny about this field is that it's the brightest field in our entire survey. So much so that when they ran a scan on it, Columbia asked, "Is there something wrong with this field?" I go, "No, not really, but that's the brightest thing you're going to see." Anyway, so in the fall of 2023, too, to kind of speed things up, we also put together a third AP130 with the help of Alan Salisky, who converted Dennis's plans into CAD designs so that we could ship them to China and have them make the parts really quickly. It was completed in October, and by February, we now had 2 scopes picking up the southern skies. Okay. Also, in January, we had our first data release. Now, if you go to mdw.astro.columbia.edu, you can download 238 fields of our survey from data release 0. And this swath covers that Orion area all the way up through, a little to the south, east, and northwest. You'll see in just a moment. Here you can, download each of the calibrated and stacked FITS files and do whatever you want. Make your own mosaic. Have fun. Okay. It's really hard to see here, but that's the footprint of the data release. You actually get a lot of my favorite parts of the sky in this particular section here. In the future, our data is all going to be available through the MAST portal. The same place where you're able to download the Hubble or the Webb Space Telescope data. There's a lot of requirements that we have to jump through, like The file naming conventions is difficult, but we'll manage it, you know. I'm just mostly concerned with getting the project done, and we seem to be just within a year of it. And if all goes according to plan, I was wrong about 10 years. It looks like it's 9. So our next data release is going to be everything that we've shot from 0 declination all the way to 90 north. And that should be coming this fall or early in the winter. Here's a really interesting animation. One of the Columbia students put together an animation showing you all the fields as they accumulated. It doesn't show you the actual pictures, but you'll get the idea here. And now that we're in the south, that's how much we've got to date. So we're almost complete. The little yellow squares and reds, they're technically completed, but we'd like to get slightly better data in those fields. Maybe the full width half max wasn't quite where we'd like it, or perhaps there's a little bit more moonlight in the gradient. Okay, but we've slowly been cleaning it up. This is our map as we've been working on, you know, where the sun's positioned versus, that's the star over there, versus what we can target. And just this week, we began collecting some data around the Large Magellanic Cloud. Not enough that I can show you because it's the edge. I'm really looking forward to getting the Magellanic Clouds myself. And just completing this whole thing. And it looks like, if again, August 2025 would perhaps be the closing date. And that's all I got. Any questions? Thank you. Right here?
So I have barely a year's worth of experience, and it is like mind-blowing.
Uh-huh.
I mean, you're seeing stuff that nobody in history has seen before. It's pretty incredible.
Yeah, I think some have seen it, but, you know, maybe in the amateur community.
In terms of the scope, right?
Right.
So my question is, if you were to start again today, and thinking about, you know, crowdsourcing and the equipment that's available that, you know, the average needs today,
Mm-hmm.
how would you do things differently? And I'm sort of thinking in particular of the approach that the Dragonfly took.
Mm-hmm.
Sort of like off-the-shelf, you know, lenses that are acquirable by mail and so forth.
Well, it's all based on on what your funding is going to yield. I mean, that's got to be very expensive. I mean, if I were to do it again starting today, well, the first thing we would do is better cameras. You know, we got you're kind of locked into your equipment when you start a survey because you can't change your telescope or your detector midway. It's not going to match. I mean, the PL, the KAF or KAI 16803 was kind of the bee's knees in 2016, but not very long afterwards, you know, 2 or 3 years ago, the CMOS cameras really were coming of age, and they solved the issue of amp glow and other issues, and now they're way more sensitive than CCDs were. So that would be my first change. But yeah, the Dragonfly array, that's a really, really cool project. But are they mapping the sky? I think they're doing targets of interest. It's a very wide field. The cool part about the way the Dragonfly operates is it has, 48 lenses looking at the same field. So in 1 hour, you can get 48 hours of data. But, you know, you pay for it. Like that whole setup probably costs several $1 million.
But that seems like if you were to average that out across multiple observers, you know, you could do a project like this maybe using crowdsourcing.
Perhaps. That'd be a lot of funds.
A lot of bureaucracy.
Yeah, it is. Even just us together plus having other people brought in. It's there's a lot of personalities involved.
You say those are the lenses, the Canon lenses that Dragonfly are using, they are not off the shelf.
Yeah.
They started out with off the shelf, but because of the image
So this sounds like a discussion to be had privately. There are other people
Yeah,
waiting
questions.
to ask questions in the back there.
Okay, thanks. Right here?
I'm a member of the American National Society for Age Protected Astronomy and Space Science.
Okay.
We've been dealing with for quite a while are the large satellite constellations. To what extent have those contaminated images before you can go back and re-image?
They haven't, because we planned on satellites being a problem. Satellites, airplanes, we're amateurs, you know. We stack 12 images for the purpose of rejecting satellite trails or variants, things like that. Things we don't want in our data. And that also means, like, maybe some asteroids we're going to eliminate, although you don't pick up a lot of that stuff through a narrowband filter. Okay, but yes, we have seen a lot of growth in the satellites in our images, but you know, they're worst shortly after sunset and shortly before the sunrise. So generally, I'll see the most satellite trails in those images, and almost always with our 12 images stacked and using a sigma rejection algorithm, it will almost completely remove all of even the brightest satellites. Occasionally, in a big bright airplane, I might have to reshoot that one. But satellites aren't the worst offenders in that aspect.
Now that you're working with the students at Columbia, are there any changes to the imaging plan to make astrometry or photometry more precise or easier in the Southern Hemisphere?
No. We had changed how we were approaching fields, try and target a field and see it to completion. But, you know, as we're bringing multiple scopes online, I mean, yeah, we only have a year or so left to do this. So, again, the detection of hydrogen and alpha was the highest priority. The photometry and astrometry that you can still glean from those. I forgot to mention, all of our subframes are going to become available, so you'll be able to do all of that with all of these. Our first data release only released the combined and sigma rejected stacked image. Our DR1 is going to include all of the sub exposures. Have fun.
Two quick questions. One, is this all self-funded? And if not, how are you paying for all of this incredible research?
It was self-funded. I wouldn't say it was myself. David Middleman did very well. He was an investment banker, I guess, and he, for a long time, was in charge of Harvard's endowment, and he had, yeah. So.
Okay. And then the other question I have is, once you finish, are you going to go back and do it all again to get dynamics, or are you going to switch wavebands and do the next thing?
No. I think 9 years on a project is enough. So you leave it to other people. In fact, almost every time I've talked about the survey, somebody has asked me, am I going to do an 03 survey? I'm not, but I know there's one in progress right now, which will complement our project.
Over here. Mm-hmm. But following up on that, have you learned about how the hydrogen alpha sky changes over time?
No, not really. The changes on our image scale is not really detectable. I mean, we're not looking for what do they call that? Things that are changing, really. I mean, and we're taking a snapshot of the sky. I mean, like I said, I was kind of excited to I often look for moving stars in our fields of view, okay? Because at least the stars will all be picked up if comets and only the brightest comets show up in the H-alpha filter, by the way. I have picked up a few that way, but no discoveries. So, yeah, we aren't seeing big changes in the H-alpha sky. But again, I haven't been able to sit down and really study our data. I'm mostly just keeping up with it right now. I mean, I had a lot more time to do a lot of stacking before we moved scopes to the south, and now I'm spending about 3 hours every morning calibrating and reducing data.
Objects like M1, of course, are detectably changing in size,
Yes.
but that's a very small scale thing that you won't see probably.
No. Larger scopes pick that up. In fact, there's a lot of really interesting animations I've seen over the years from people like Adam Block, who have been imaging the sky for about 20 years with large telescopes. They can see like the M1 expanding, things like that. I don't think we've seen any new nebula appear during our project, but again, I haven't really dug into it that closely.
Have you covered the field of supernova 1987 in the southern sky yet?
Not yet. Again, that's in the Large Magellanic Cloud, which we are just starting to hit right now. Looking forward to it, though.
What do you know about that arc, the long arc?
Not a whole lot yet. It's suspected that it might be like a bow shock from an ancient nearby supernova or nova. I'm involved in a project to try and find more of those right now. So a team that I've been involved with, I was party to the discovery of that O3 nebula near M31 last year. Some of the same players are investigating this to try and really map out how the extent of this arc and see if there's any other remnants in the vicinity. There's a couple of tantalizing positions in I think it's in Butes or in that part of the sky. Don't quote me yet.
I'm going to sort of pull this down.
Okay.
You're welcome to be around and answer further questions. It is nominally lunchtime. Richard Sanderson's presentation starts at 1 o'clock.
Mm-hmm.
And I wanted to just say, it looks to me like that arc is really the Little Dipper trying to pour water into the Big Dipper, but it missed.
Oops.
Anyway, thank you for a wonderful talk.
Thank you for your time.
Beautiful.